welcome for being here. I mean, it has been a long day so far. I actually took a nap for 10 minutes, so I know it's very hard. But hopefully this conference you will learn something, you will be inspired, you will go back with something new in your head, something you want to try. My intention here is not only to teach you the basics of something, but also to inspire you to look at those things on your own. So experiment and see what you can do. Because every problem seems to be incredibly complicated, but when you start doing it, you discover that it's actually not that complicated. It's quite simple. So it's just, I would like just to be the one that pushes you in the right direction if you want, okay? So today, we'll be talking about distributed systems and a particular aspect of them. Let's first introduce myself. My name is Bruno Bossola. I'm Italian, and I'm developing since 1988. I started very early with assembler and C, and then all the way down to whatever we use now, Java, Scala, whatever. I am a Java champion actually from 2005, so I know Java pretty well. I've been using extreme programming from the very start, so I know what Agile is. And at the moment, I'm working on a startup of myself, which is called Theorem, which we are trying to avoid things like happen to Equifax. Anybody know Equifax? 150 million users compromised, and the company said, "Oh, it's open source fault." No. It's your fault because you didn't check what you were doing. But that's another story. So that's my handle, Twitter handle. So if you tweet about me, I will be very happy. That helps me to build this fake reputation that I'm carrying around, no? Pretending to be somebody that I'm not. So if you tweet about me, that would be great. Again, it's good to be again in Prague. I've been here last year, and I like the city. I like you people, so all amazing. Right, let's get to it. So what we're going to discuss today is generally about distributed programming. We will have a look with a few slides about what does it mean, how does it work, and then we will tackle, the CAP theorem, which is, well, when you say theorem, oh my God, it's going to be complicated and boring. No, I mean, it's going to be okay. And it's actually something that you will be able to use yourself when you are interviewed by somebody and they ask you about a distributed system. You can, CAP theorem, I know about that. And I mean, hopefully you will understand what it is and how it works. And that will be a big advantage about your competition on an interview. So it's definitely CV and interview materials. So listen to it. And if something is not clear, please come back to me by my Twitter handle or catch me around. I will be here also tomorrow and ask me any questions. And we will see live demos and code. Depends on the time. How fast I am, we can see more code or less code, and more demo, less demos. And then we have probably no QA session, but yeah, we'll see about it. Now, the first problem is, do we need distributed programming? Is it something that we need? So why we should bother about this? Why we should care? Who gives a flying, I cannot say that, it's recorded. Why? And the problem is, well, if you have one of these, in your room or somewhere, you probably don't need to care. Because this is something that gives the power of 93,000 trillion calculation per second, so 93 petaflops, I guess. So 10 million processing cores, 4,000 nodes, and by the way, it runs on Linux. So just saying, nothing against Windows, fantastic. Beautiful. Windows is brilliant. In case somebody from Microsoft is looking at this. Right, I really believe it. Now, in reality, you may not have that thing. And then what you have to do, you have to find a way to run your complicated software in a much more scalable system. So in a system where you don't have a big CPU, you don't have a big disk, you don't have a big things, but you have a lot of small things. So rather than having one big multivac computer, whatever the name could be, you have a lot of disposable PCs, or even worse than that. You know, actually Google started building their own hardware. So for the Google Cloud, they don't build that. They don't buy anything. They build their own very, very, very simple machines. And they literally, they broke, they change it, they replace it, they buy new ones. So it's all, they don't care because they have so many of them and they're so easily replaceable, which doesn't make sense to invest a lot of, you know, maintenance of them. It's broken, okay, get another one, done, no, $10. We actually, when I was in 2 companies ago, we built our own rack, our own cloud, if you want, makes of Raspberry Pis. It's amazing what you can do. So it's fantastic. You just pick up a lot of Raspberry Pis, you put it one over the other, you connect it to a switch, and you have a distributed system. Magic. It's amazing. So anyway, going back to the point, we need to deal with 2 tasks, 2 problems here: storage and computation. So storage, you cannot have a big disk, but you have a lot of smaller disks. And computation, you don't have a big CPU, you have a lot of smaller CPUs. No? And the problem is, how do we scale, and how do we fake the fact that you have, instead of having one big computer, you have a lot of small ones. No? How do you manage that? Because in your view, you want to have a big computer, but you don't have the money to buy that thing. So you buy a lot of smaller computers. No? How do you fake it? No? All right. And in this presentation, we will look at one side of this equation, which is the storage part. So how do we fake the storage? So how do we see a million of different disks like one single disk? No? A million storage like one big storage. We have to deal with 3 basic properties I need to explain you: scalability, availability, and consistency. All right? Now, scalability is the ability of a system to handle his growth, no, and to be enlarged to accommodate new growth. So you need more space, and basically more users are coming, and you just add more space like this. No, your system should be able to deal with this situation, no, and without giving any problem to anybody. So simply happens: you need more space, you add more machines. That's it. So, but the problem is, how do we do this scaling? How does it work? The first thing that we should think about is partitioning our data. So rather than having all the data in one single bucket, we separate them in different buckets. So imagine we have this. So at the moment, we have a big database with these 3 types of data. No? Triangle, circle, and I don't know what is that. Sorry. My English is not at that level. Some other shape. No? And you need to, how do you handle that? You want to distribute them. Well, you transfer them on 3 different places. So in one place, you put the circles. In one place, you put the triangles. And in another place, you put the mystery shape. And that's good. That's good because also improves the performance. So because when I'm looking for shapes, I'm not looking for circles. And the shape query is much, much faster than the circle and vice versa. And, in a sense, it also makes the system more available because, if the circle stops working, the other 2 keeps working. But yeah, there is the problem, however, what happens if one of those stop working? So what if it becomes slower, even slower? What happens if it slows down a lot? What if it becomes unresponsive, just there doing nothing, frozen? No? You end in this situation where, nobody's really happy. And so partition is one side of the problem. The other side is replication. So what you can do now, is, well, you can do something else. What you can do something like that. So you can put on the different system different types, no? So for example, circles and triangles on one, triangles and shapes on the other, shapes and circles on the other one. So in that way, if one of those systems fail, you will be able to read from the other 2 systems. So this should be maybe it's obvious to you, but this introduces a new problem, because I mean, this is cool because you can add more server easily, so we can expand. The performance are better, even better than the situation, because we can partition the query and can do half there, so we can have more performances. And and if one fails, no problem. But there is another problem that may happen. No, what happens if? Do you know that? What is the problem? No? Yes. You use a big word, consistency, that's correct. So what happens if those two copies of your data becomes like not exactly the same? No? Like in this situation, we have certain version of the data, and everything is happily aligned. No? But then, for some reason, one system stays behind. So, in one of those shapes, has an older version. So, if for some reason we are going to ask to query that system over there, then we're going to end up with the wrong answer, probably a stale answer, an old answer. This is not good. So, the problem that you have now is that how do we make sure that all these different copies, and I put 2 here, but usually you have like plenty, how all different copies are aligned, or you're able to get a consistent response from them. We will see about that. And yeah, this is a consistency problem. So, and there are different ways to say it. So this is an example of strong consistency, so that each client at the same time has the same view of the data. This is the easiest way to say it. So you have 10 clients, and everybody, when any of them, then they do a query at the same time, they got the same response. And that's quite complicated. That's a quite complicated problem, and we'll see how we can solve that. But before we go in there, I want to anticipate, the 3 different consistency flavors. So we have strong consistency, where the one we were talking about before, so that all the operations are marked on the instances in the same order, and there's no situation where 2 replicas has a different value at the same time. Always, everything is coordinated. Magic. Never happens. Weak consistency, which is an interesting one. So basically, every system see any update, but they might see them in a different order. And you say, well, what do we do with that? I mean, how do we deal with this? It's useless. Well, sometimes can be useful. So if you think about, for example, your account, your current account, your money, your deposit in the bank. It doesn't really matter if you count, to a point. It doesn't really matter if you count first the money that you put in and the money that you get out. You always get the same total at the end. And if you're interested to the total, and there are a lot of algorithms that are interested to that, then weak consistency is a good idea. So you can use that. And it's easier to implement. But the one that we really kind of like is eventual consistency. So every replica will eventually see the same value, or all of them will eventually agree on a value, eventually. So at a certain point in time. I mean, and this is not years, so I'm talking seconds, something like that, And this is the one that is exploited the most in distributed systems. A lot of databases that you may like or not, some of them better than the others. Yeah, I will get back to you with this one. Are using this property? Well, in best ways or worst ways, it depends. Let's go back one step back, however, about availability, which is also important. Because if your database is consistent, it's perfect, and you cannot read from it, you cannot write to it, what's the point? Oh, everything is magically consistent. it's like a write-only memory, no? What do you do with that? Do you want 10 terabyte of write-only memory? I have it here. You write only, you never read from it. Everything is consistent. What do you do with that? No? So the thing is, your system must be available, and also it must be available to read and write, react correctly to a fault, and also, I think I have the other slides, yeah, and also deal with some things like performance, no? What about performance? I mean, what's the point of having consistency, or if the system is not available, if when I want to do a query, it takes 3 minutes or 5 minutes. What's the point? I'm not going to use it, no? And the same is latency, no? You know, latency is the zombie. I like the zombie metaphor. So a zombie currently, I mean, imagine a zombie bites you, and then latency is the time from the bite to when you start becoming a zombie. That's latency. And some system has a lot of latency. For example, you go and do a query against, I don't know, Singapore, a database in Singapore, you will notice a lot of latency. I mean, the speed of light is a bitch. You cannot really change it. Sometimes, no, really, I have product manager. Can it be faster? Look, we are here, so we are in Chicago. We are in Chicago. They are in Singapore. I mean, count the miles. You know, this is the speed of light. Maths. Sorry. But sometimes you're able to mitigate that with an eventually consistent system, distributed system, because you can have a copy in Chicago and a copy in Singapore, and eventually they will be consistent, hopefully. That's how we solved it. But yeah, just to say one. Now, let's go to the CAP theorem, which it works on 3 axes. So the one is consistency, no? So I want a consistent system. Every client should see the same value every time. Availability. I want an available system. When I do a query, I want to receive a proper response in a proper time without waiting years, okay? And then we have the third, which is unfortunately the one that breaks this fantastic diagram, the one that put everything at risk, which is, no, this is partition tolerance. So you want your system to be tolerant to network partitions. So what happens when, you know, the classic situation where the cleaning boy go through the server machine, trips on the electricity and detaches, not electricity, detaches a switch, no? So the network is partitioned. So half of your machine are on one side and half of your machine are on the other. How does your system react to that? When the network is partitioned in 2, split, one of the system cannot work anymore, cannot receive any connection. How does that work? And the problem with that is that you cannot have all these 3 things at once. You can only select 2. And this has been, I mean, I'm not saying that. There is a mathematical demonstration that somebody said it was debunked, but no. Sorry, that's math. It's like the speed of light. It's a bitch. And you can select only 2. And that's what the CAP theorem is about. You can select 2 of these properties, and I will show you different system that works on the different combination of those properties, okay? Right. Now, let's start from this CA system. Those systems select consistency and availability, no? But they say, well, network partition will never happen. Which is okay, you can do that. They happen, by the way, but we all know that they happen. But you know, those are called strict quorum protocols. So there is the system to reach a consensus state, so a situation where everybody agree on a value, requires all the components to be in agreement. So all the parties on the distributed system must be in agreement. Strict quorum protocols. And those are, for example, all the two-phase commit protocols. The one, for example, Oracle, the major database uses MySQL, Oracle, all the classical RDBMS are all using this. In fact, when they're placed in a distributed system, when you use a two-phase commit, if you detach one of the systems, you know, the database stopped working, will not accept writes anymore. Now, we have now AP system. So in this system, you prefer availability to consistency. And you're saying, who's going to do that? Who is the fool? Well, Amazon. Why? Think about it. So they want you to be able to buy. The most important thing is that you are buying from Amazon. And they cannot tolerate the fact that if one of the database goes down, you are not able to buy. You cannot put the things in your basket. No? Oh, you want to buy something, you put it in the basket. And this means changing something on the database, right? And they prefer to be in a situation where you have 2 items in your basket rather than 1 item. So it's okay for them to be in an inconsistent situation, and then they will deal with it later. You will receive 2 items. You say, why I receive 2 items? You call the call center, and they say, oh, you can keep them. We don't care, keep them. Happened to me. I didn't notice. It just happened. And that's okay, because they save much more doing that than trying to set up a consistent system. They save much more with that. So that's what they do. And this was explored by a famous paper from, I don't remember the name of the CTO, that was produced on Dynamo, that was read by somebody at Facebook. Wasn't really I can say that. So they really didn't understand it, so they built Cassandra. Yeah, sorry. It's good. No, Cassandra is good. Cassandra is a great database. Fantastic. And somebody in Facebook is watching. Right. Now, the other system are this one, CP system, where you want consistency and partition tolerance. So, and those are called majority quorums. Or the previous are sloppy quorums. Those are majority quorums. They require a majority to agree on a value. So, in presence of a partition, of a network partition, part of the system might not be working, but most of the system will be working. No? And so you have an availability problem. So where you cut a partition, you divide, the classic giant or Godzilla goes through the ocean, trips on the cable, no? Everybody's tripping these days. And, no? And they break the connection between USA and Europe. And USA has more servers. Then USA will continue to work. Network will be in read-only. That's what those systems are doing. And those are majority quorum. Now, Zookeeper and Google Spanner, for example. Now, let's go to, I just saw this one. Let's go to do some coding, all right? So this is the end of the slides, sorry. If you don't understand code, you can leave, no, you can stay even. You can stay even if you don't understand code, because we're gonna see demo, don't worry. So we're gonna write, well, I prepared one at home earlier, no, you know what I mean? But we're gonna see the code of a key value store. I used NodeJS, all this code is on GitHub, you will see the links on the slides. And we will code all the 3 different flavors, all the 3 different systems, so we understand live what happens, no, in presence of network partitions. We will have, I think, 4 nodes, fully replicated, but we will not have any sharding, so don't worry about the sharding now. And we will kill server, we will partition a network and see what happens. Now, this works on my machine, so if you have any internet problem, it's on you. I'm not touching your network. Okay, I'm using IP tables to change my machine. It's a simulation. All right. Now, so the general design, 25 minutes. Let's go to the demo, and then we go back to the design maybe. But yeah, the general design is this one. So basically, you have a storage API that you can access via REST interface, and you can get a value or set a value given his key. So a class is key value store. And this key value store stays on top of the database here, and the database is just is in memory. So sorry, didn't have time to use a real database. And there are several APIs used by the protocol that we're gonna use. So we're gonna use when we're gonna change the system, we can use different APIs. That's pretty much it. So let's see a CA key value store. So this will use a two-phase commit, classic protocol. I implemented it. It's very easy. What happens is that we're going to see live. And it's not partition tolerant at all. So you stop, you partition the network and the system will stop working. Right. Here we go. I hope, can you see it? Yes? Yes. Yeah? Yeah, you can. Good. So this is the code you can find on GitHub. So basically, there is a different folder for each of the protocol that will implement the protocol differently. 25 minutes. Okay. So let's start with this. So the two-phase commit, it works this way. So I want to, write a value, write a value, and then it happens that the server that I will contact will get in touch with all the other server and will propose the change, no? And the other server will agree on the change, and then the initial server will say, okay, commit, and all the servers will commit. So this is the reason why it's called two phases. First there is a proposal, and everybody has to agree, and then there is a final commit when everybody say, okay, we store it. Okay? So basically, the first situation you put in a temporary transaction log, and then you move it to the real transaction log. And I mean, of course, the system can say, no, I don't agree. If there is, for example, a concurrent client that is trying to change the same key, that will not agree. So this is, okay, it's already in IC mode, yes, two-phase commit. So I have some simple script here. So at any point in time, I can dump the database, which is currently is empty. So we have 1, 2, 3, 4 servers, okay? One of them is slow. I don't remember which one. Let me just see which one is the slow one. Because it says when it starts. Oh, yeah. The one on top, the 3004 is the slow one. All these servers are on different ports, okay? So 3004, 2003, 2002, 2001. So what I can do now, I can set a value, no? And I call this server. So as you can see, a proposal started. So I've tried to set city London. So the key is London, the value is something. Oh no, the key is city and the value is London something because I live in London. So, right? So we start with a proposal, then it send the proposal to all the peers. Then when all the peers are in agreement, it will send a commit to the peers and they'll all are in agreement. You say 200, 200, 200 means in HTTP, I agree, I agree, I agree, I agree, I agree, I agree. Okay? Easy. And now if we dump the database, we will see that there is a certain, value inside. If I do a get value, and I ask, for example, I don't know, it's going to ask probably this one. Yeah. So it will not even bother to ask the others because he knows by a fact that the system is aligned. So there is no possibility they have different value in the database. No. So I ask the key city and I get the value from this server. Oh, good? Yeah? I lost you already? No, that's easy. Yeah? Yeah? Good. Fantastic. Now, imagine now, what happens if we kill one of those servers? So imagine that I kill this one. I don't like this one. All right. You die. No? Sorry. So what happens now? I try to set a value, no? And they will struggle. Oh no, I wasn't able to do that. So, I started sending the proposal, but then only 2 of them answered. You say null 200, 200. So I wasn't able to contact that one, no? And for that reason, it sent a rollback. No, this is not going to happen. So from this moment on, I cannot write. So this is dead. I cannot do anything. Only if I restart the server, then I will be able to write again. Okay? This is a limitation of the system. The same if I partition the network. I'm using IP table. So I can stop that. I don't know why I'm against that server, but I really hate him. So I can stop that server. It's the 3002, right? Freeze 3002. So I just frozen via IP tables that one. So you can see if it's not going to receive any command. Again, if I try to set a value now, no? It will hang for a while, and then it will send a rollback and fail. That's it. So this one is not working. So I have to unfreeze it. I think I have an unfreeze, hopefully. Yes, I have. Yay. So I have to unfreeze it. And then you see this guy is starting receiving the packet that he lost. So he's starting getting packets again. And you know, the network is also a bitch. It will send you the packets in wrong order, one here, one there. It can act very, very, very badly. Okay? And now, from this moment on, I hope that now if I set a value, yeah, it's still alive. No, still not alive. He's not contacting it. Well, I think he's not contacting. He's still receiving 400 from this guy. It should recover at a point because I unfrozen the network, but it's still not working. But you know, this is the problem. When you have this kind of network partition, you don't know when your system will come back to life. And this is a big issue. Now, let's go back to the next one. The value store using AP. So AP is an eventually consistent design. And in this design, when you write, you use basically a sloppy quorum approach. So if 2 people come back to you and says it's okay, even if you are 4 people. Or when you read, if you have an answer from one of your peers, it's okay. That confirms yours, it's okay. You don't have to ask everybody. And this is a sloppy quorum. You ask to some people. And you know, one problem that the default Cassandra configuration, I don't remember if in read or write, it asks only to 1 peer. So it's very weird. But let's go back and change the system configuration in AP mode. Now, oops, sorry. Now you see now it's using sloppy quorum. So now if I ask to set a value, it will be also very fast because you remember the sloppy one, the slow one over there, no? The slow one was affecting the performance of the whole system when we were using a two-phase commit because the master has to ask to everybody, no? Are you okay? Are you okay? Are you okay? And the slower one were causing slowness in the answer. Now it's very fast. It's fast. Why? Because this guy is just asking to 1 peer. Look at what happened here. I do the command. Help, done. And after he receives the answers. So he just need 1 of his peers to confirm that it was done, and that's okay. And then eventually he will distribute the update to the other guys. And in read, well, in read you may have a different quorum. I think in read I have 2 people quorum. So in read it will ask for 2 peers in order to send the response. So if I kill this one, bye. I really hate this guy. Now the system still works. I'm still getting information. All good. And I can change values. Everything works. When this guy comes up, what is the protocol? The protocol is that when this guy comes up, no, and I ask a read, at that time there will be a reconciliation. So the system will try to reconcile the value looking at certain things. So let me see a get value. All right. You see what happened here. So I ask the system the value, and he receives 2 answers. 1 positive and 1 400. I don't know what they're talking about. 404. And HTTP says not found. No? You see there. And it was inconclusive. So this guy waited for the next answer. And the next answer was another 200. Okay, I have 2 people that agrees with me on the value. At that point, what did he do? To the guy that didn't agree, very democratically, he said, this is the new value, suck it. No? This is what he did. So he sent a repair command to the other guy. And now everybody, magically, for the magic of democracy, everybody agree on the same value. Another thing that this thing uses is this TS. You saw what TS down there? Is a timestamp. So many of the systems, like the one that I naively wrote, they use the time system to determine, the timestamp, sorry, to determine how fresh was the value. So when it has 2 different values, it says, no, this is fresher. No, it does that. Okay? So this is an important thing to do, especially in largely distributed system where a lot of partition may happen. It may be complicated to reach an agreement. So you associate a timestamp with the with the value. Okay? So now the same happens even if we freeze now this guy. So let's freeze it. All right. Why am I freezing all this guy? And now let's, oh my God, let's clean. All right. This guy is not reacting. So I set a value. All good. Done. I get a value. All good. Done. Nobody cares about this guy. When I don't know what. When we unfreeze the guy, no? Here we go. Unfreeze. All right. Now, you see, this guy starts receiving weird things, but eventually he will agree on the same value. I already received the repair, by the way, automatically. I don't know how that happened. Magic. So it's not, everybody's now agreeing on the same value. No? Because the system self-repairs itself. No? When something happens, this system is able to self-repair itself. Now, if you use Cassandra, change your configuration to 2 in read, 2 in write for the quorum. Thank you very much. You will make a favor to a lot of people. Trust me, do that. 2 in read, 2 in write. Because Cassandra usually have at least 3 nodes. So at least a double agreement. Okay. Now, you were going to say, oh, this is cool. I could have thought about that. No? Yeah, I'm a software developer. I could have thought about that. Yeah, true. But if you read the original paper by the guys in Amazon, you will discover that it's slightly more complicated than the way that I presented it. But still, it's something that works when you have this particular problem. All right? Now, let's go back to the value stores in CP mode. So in CP mode, you want to have a majority. So whenever you set or get an well, actually, when you set an information, let's say, you want to have a majority. So you don't want to have a situation where there is this sloppy quorum. You have to have a majority. And if anybody disagrees, it means that it's probably disconnected and we don't care. But eventually, it will come to an agreement. And there are a couple of very complicated algorithms that are dealing with this quorum problem, strict quorum problem. One is Paxos, which is very, very complicated, and I wasn't able to make an example of that, I'm sorry. And then there is Raft, which is much, much easier. And I made an example with Raft. But, I mean, a lot of people are using Raft, really. Not a lot of people are using Paxos. Maybe Spanner is using Paxos. No, I don't remember. But Raft is much, much easier. So I think Zookeeper is I don't know. I don't remember now. I want to say stupid things, but so I will shut up. So, okay, let's keep that. We'll come back to that later. So what happens when we use a CP protocol? Ooh. Right. When you're using a CP protocol, there is usually an election. So in this system, you will have somebody who is a leader, who is get elected. So when the system starts, there will be no, let me show it again. When the system starts, there are no leaders, but then the system will elect a leader somehow. Somebody will be elected to a leader, because when the system starts, everybody will try to be elected as a leader, like a politician in Italy, no? Everybody wants to be in power and want to be elected. Everybody will try. And the first guy who will require the majority of votes, he will be the leader. From that point in time, the leader will start updating all the other guys. So he will send what is called a tick to all the other guys, continuously, tick, 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 tick. And all the communication will happen on this tick, on this transfer. That here I slow it down a lot, so it's every second. But normally it's quite fast. So, so you see, this was elected, and the election results are there. A lot of people voted for him. He's a good guy. So yeah, you are my leader. That's it. No? And you see all the other guys are obeying. They're receiving the bit from the leader. So the leader is updating there. The leader is updating, where's my cursor? The leader is updating here, no? And the other guys are receiving the update, no? Now, whenever I ask the system to store a value, my request will be forwarded to the leader. The leader will send the request over the bit, and only when he receives the OK, he will say, OK, it's good. But he needs the request to receive the OK only from a majority. He doesn't need to receive it from all of them. At the same time, he wants a majority. He doesn't want to have a sloppy 2 people or 1 person. Yeah, it's OK, don't worry. No? Now, let's see what happens. I'm going to set in a value. So the database is currently empty. Yes. OK. I'm going to set a value. I think I will get in touch with this guy, which is the leader. So there will be no forwarding. Here we go. And you know the value will be sent across over the bit. So over the bit, you will see the value is sent to all the guys, and all the guys will update themselves based on the value received on the bit. Now, what happens if something goes wrong and the leader dies? Oh no! Oh, there's an update available. That's good to know. Thank you. No, the leader is dead. Long live to the leader. Long life to the leader. He's over there now. The leader is the slow one. Oh my God, the one I hate. So the leader is that guy over there, right? So that guy suddenly became the leader because it was an election, and I don't know why the guys decided to elect him, but that's what happens when you use random, which is currently what democracy is doing to us now. Yeah. Whatever. But if this guy, when this guy comes up again, no, hopefully at a certain point in time, they will rejoin the cluster, and they will. And what happens is that he will receive an update about the status of the system. So it will ask basically to the system, well, the last time I heard you, it was at this time. What happened between that time and now? And it will receive all the changes that happened during that time, right? So you see here, history received, and you received this. This is a transaction log that happened during that time. And how do they measure time, this system? They measure based on 2 things, the term and the tick. The tick increases every time the server sends a bit. And the term changes at every election. So if we now check the database, you will see that for each value, now we have 1 value, sorry. For each value, there is a term and a tick. So this value was set at the first term, and the tick was 151. So if now I change and I set another value, no, and I then dump the database again, you will see that now the term and the tick are updated. This is how they resolve inconsistency in the data. They use the term and the tick to do that. So what happens when I freeze something? Same thing. I'm going to freeze my favorite. So this guy is now frozen. Let's verify it. Yes. You see, now this guy is frozen. So his network has been partitioned. And what he's going to do? He say, oh, I don't have a leader anymore. No? Because he's not receiving the bit. The tick and the bit is not receiving it. So I want to be elected. Let's start an election. Yeah. And nobody cares. He's alone. Poor guy. No, like a lemon. Alone there. Nobody gives a crap about him. No? But he's still trying. Yeah, I'm trying again. Yeah, now in term 25, he's going to start doing his own terms of election and go ahead, go in the future. And nobody will think about him. No? Well, but the system will still be working. So the rest of the system will work. And you can see the other guys are responding nicely. And I can see the database and everything. All good. Now, let's unfreeze the guy. Dun, dun, dun. There we go. Now, it's going to receive a lot of network packets, random ones. And then, you know, it eventually will align of the right term and the right tick. And it will align and go back. It will ask a transaction log, and we receive everything. So this is the magic of this approach. So even if the Godzilla guy goes into the ocean and trip on the cable and destroy the table, eventually it will come back to the same value. It is the beauty of this thing. So now everything works. You can see, hopefully, I'm just saying, yeah. You see, the other guys, no, were receiving the votes that this guy sent before, but they were ignoring it because they were in the beat. They knew they were already a leader, no? So they didn't notice that. They say, oh yeah, I'm receiving that, but yeah, somebody's misbehaving here, no? And that's a Raft protocol. There is a very nice, in the slides, in the last slide, only 4 minutes now, in the last slide, you will find a link to a very nice explanation on the Raft protocol. So if this wasn't easy enough, or you don't want to try this at home, you can try. You just need Linux to freeze and freeze, but you can kill at home, no worries. So there's a very nice visualization of the Raft protocol. Okay? So this is a majority protocol. We need a consensus of a majority of the servers. Okay? I think, oh, yeah. This code, sorry. It's 9 months since I wrote this code. I never refactored it. It's very bad. So if you go on GitHub, please accept my apologies in advance. No, sorry. It's like when when my developers, probably when I ask them, when you write a comment, say sorry. Because it means that you didn't know how to properly write the method name. So just apologize. Sorry, I didn't know how to explain this, so I put a comment to clean it up. The same thing here, sorry in advance. All right, so what next for you? So 3 minutes. What next for you is learn the lingo and the basics. So if you didn't understand enough of this, go on GitHub, check the code, and go on Wikipedia, learn about these protocols. It's easy and makes a difference. You understand things more. You understand more. It's so nice to learn new things, and I think you should do it. You should start playing. So you can use my code. You can write your code. I'm sure that in some of your system you have a distribution problem. Maybe you don't see it now, but it will happen. And you may start experimenting and think about it. And it's not rocket science. It's easy. I made all the code of this example in 2 days, and 12, 14 hours. Let's make it 3 days, no? Because I have to fix some bugs. But it's not that complicated, so you can do it. And I wrote it in JavaScript. I'm not a JavaScript developer at all. I'm a Java developer. Now, Amazon Dynamo, that's the paper that I was talking about. This is the Raft consensus algorithm visualized, very nice. And this is my code. If you can tweet about me, thank you very much. Please do that. And if you can have your vote, there is an application. You can vote for me. That's fantastic. If there's stars or something, put as many stars as you have. No, well, whatever stars you think I deserve. Okay. Now I have 2 minutes, I guess, for questions, if there is any. Yeah, no questions.
I have a question to this Twophase protocol.
Yes.
This proposal is accepted, and then crash occurs. Then the whole system is blocked until some intervention, or how is it resolved?
Well, there usually are timeouts. So the transaction log is is put in a temporary state, and you have this proposal there, and the proposal lasts for a while, and after that is expired, it will be rolled back. So it's like a normal commit. So you open the transaction, no? You put a record into a table, but that doesn't really happen to all the other guys until you said commit.
Yes, but this commit might not reach every member of the party.
Sorry, say again?
If the commit does not reach every member of the party.
Yeah, it's the same thing. It will not be published in the transaction log of anybody until everybody had agreed. So everybody has to agree to the proposal and to the commit. And then it becomes part of the normal transaction log, and you will see the change. Right. Anybody else? Anybody that dares? Nobody? That's great, because I really need a coffee. Again, thank you very much. It was a pleasure. I hope I helped you a bit. Thank you.